Welcome back to Key Safety Talks. Today we're diving into something that's all around us, but we might not always think about. It's hydrostatics and hydraulics. The science of fluids, how they act when they're still and when they're moving.
You hit the nail on the head. We do take fluids for granted, don't we? But they're a big deal for our lives and for staying safe. I mean, think about it. Everything from the water we drink to the hydraulic system that control heavy machinery. We got to understand how fluids work.
Okay, so let's break it down. What exactly the difference between hydrostatics and hydraulics? It's all about fluids, right?
Yeah.
I'm a little fuzzy on the specifics.
Sure. You can think of it this way. Hydrostatics is like looking at a calm pond on a peaceful day. Everything's still, the water's at rest. But on the other hand, hydraulics is like that rushing river you wouldn't want to raft on. Lots of movement and energy.
Ah, got it. One's still, one's flowing. Makes sense. But now I'm remembering back to high school physics. Didn't pressure play a big role in how fluids behave? Can you remind me about that?
Absolutely. Pressure is basically the force a fluid exerts over a specific area. Think of it as how much push that fluid has at any point. And gravity really affects this push, this pressure.
So if I have a tall container full of water, the pressure at the bottom would be higher than the top because there's more water pushing down, right?
Exactly. And that leads us to a really interesting point. The pressure from a column of water doesn't care about the shape of the container. It only depends on the height of that water column.
Well, wait a minute, really? So like a tall, skinny container and a wide, shallow one, both filled to the same height with water. The pressure at the bottom is the same. That's kind of hard to wrap my head around.
I know, right? It seems counterintuitive.
Yeah.
But that's hydrostatics for ya. It challenges what we think we know. And knowing this is super important for building structures that can handle the crazy pressure of water. Think about dams, for instance. They need to be insanely strong to hold back all that water.
You're right. Now that you mention dams, it makes me think of those terrifying dam failures you see on the news. Didn't one of the worst engineering disasters ever involve a dam collapsing because they messed up the hydrostatic pressure calculations?
You're probably thinking of the Teton Dam collapse. Happened back in 1976 in Idaho. It was a horrible event. Lots of flooding and people lost their lives.
That's the one. It's a scary reminder of just how powerful water can be, especially when we underestimate it. Could you break down what happened with the Teton Dam and how hydrostatic pressure played a role?
Of course. So the Teton Dam was an earthen dam. They built it to create a reservoir for irrigation and to help control flooding. But even while they were building it, there were already some red flags. The rock formations in the area were complicated, very permeable, and, well, the design didn't really account for that properly.
So even before it was finished, there were doubts about whether it could handle the pressure.
Yeah, there were some warning signs. And when they started filling the reservoir, those doubts became a reality. Cracks showed up in the dam and water started seeping through. It was pretty clear that the hydrostatic pressure was winning. The dam just couldn't hold it back.
And sadly, they didn't act on those warnings in time.
Unfortunately not. The dam ended up giving way, releasing a massive amount of water that flooded the Snake River Valley. The force of that water was unbelievable. It literally carved out canyons and moved tons and tons of earth, changing the landscape completely.
A harsh lesson that we can't underestimate the power of hydrostatic pressure, especially when we're building structures that interact with water. A small miscalculation can have disastrous consequences.
No doubt about it. Thorough geological surveys, careful design reviews, and built-in safety factors are non-negotiable.
Okay, we've seen how crucial hydrostatic pressure is when fluids are at rest. But what about when they start moving? What happens with pressure in hydraulic systems?
Think about your garden hose. When you turn the water on, it flows through the hose at a certain pressure and speed. Now, if you cover part of the end with your thumb, you're basically squeezing that flow, right?
Oh yeah, I've done that a million times. Trying to make the water spray farther, the water shoots out with more speed. But what about the pressure? What's happening there?
Well, that's where the concept of head comes in. It's a way to measure the energy of the fluid at a particular spot. We have pressure head, which is basically how high a column of still water would have to be to create the same pressure as your moving water.
Okay, so higher pressure head equals more potential energy, more power to push that water further.
Exactly. But when you constrict the hose with your thumb, you're actually lowering that pressure head, but increasing the velocity head.
Velocity head. What's that now?
Think of velocity head as representing the kinetic energy, the movement energy of your flowing water. It basically tells us how fast the water is moving. By squeezing the flow, you're forcing the water to move faster, which bumps up its velocity head.
So it's a trade-off. More speed, less pressure.
You got it. It's all about balance. And this pressure and flow rate balance is super important when designing any system that uses fluids to do work.
I'm still trying to wrap my head around this head concept. Can you give me another example?
Sure, picture a water tower. The water at the top has a bunch of potential energy because of its height, right? That's its pressure head. As that water flows down through pipes, some of that potential energy turns into kinetic energy, increasing its velocity head.
So as the water travels, it loses some of its push, but gains speed.
You got it. And engineers need to carefully figure out both pressure head and velocity head to make sure the water reaches your faucet with enough pressure to actually be useful.
That's wild. It's like there's this whole hidden world of forces and energy happening every time we turn on a faucet.
You said it, and that's just the tip of the iceberg in the world of fluids. We've just dipped our toes into pressure, flow, and how they all work together.
Well, I'm hooked. I want to learn more. You said earlier that knowing how fluids behave when they escape containers is a safety thing too. Tell me about that.
All right, that brings us to Torricelli's law. Sounds complicated, but it's actually pretty straightforward. Basically, it says that the speed of a fluid flowing out of a hole in a container depends on the height of the fluid above that hole.
Okay, so let me see if I got this. If I have a full milk carton and punch a hole near the bottom, the milk will spray out faster than if the carton was almost empty.
Exactly. The height of the milk, what we call the head, is greater when it's full, so there's more pressure pushing that milk out.
That makes sense. I'm guessing this isn't just about milk cartons, though.
You're right, it's not just milk cartons. Engineers use Torricelli's law to figure out important stuff, like how fast liquid will drain from a damaged tank, or how fast water would rush out of a broken pipe. This info is critical for designing safety systems and emergency plans.
So, like, if there's a leak in a chemical tank, knowing how fast that chemical will escape helps emergency responders contain it better.
Exactly. And sometimes knowing that speed can mean life or death. Think about a fire in a building with sprinklers. Knowing the flow rate from those sprinkler heads is essential to making sure the fire is put out quickly and effectively.
Wow. A simple principle like Torricelli's law has huge implications for safety.
It really does. And that's what's so cool about fluid mechanics. It's full of these hidden connections. Seemingly simple things have huge real-world effects.
Okay, so we've covered pressure, flow, and how fluids act when they escape. What else should we know about how they move?
Well, fluids can flow in two main ways: laminar and turbulent.
Ooh, those words are ringing a bell. But a refresher would be great. What's the difference and why does it matter?
Picture a river flowing smoothly. The water glides along in these parallel layers, barely mixing. That's laminar flow. Smooth, predictable, efficient.
So laminar flow is like a parade. Everyone's in perfect formation.
That's a great way to put it. Now imagine that same river during a flash flood. The water is churning and chaotic with whirlpools and eddies all over the place. That's turbulent flow.
So turbulent flow is more like a mosh pit at a concert. Everyone's bumping into each other.
That's a great analogy. And just like sometimes you want a parade and sometimes you want a mosh pit, there are times when each flow is better.
So when would we want each type?
Well, a lot of times in engineering, we want that smooth, predictable laminar flow because it's more efficient and less wasteful. Think about oil or gas flowing through pipelines. We want it to be smooth to avoid energy loss from friction.
Smoother means less energy wasted. Right?
Yep. And less wear and tear on the pipes themselves. But sometimes you actually need turbulent flow. For example, in a car engine, you want the air and fuel to mix really well for the engine to work properly.
So turbulent flow helps mix things up.
It does. Sometimes we even intentionally create turbulence to make things work better. In chemical reactors, for instance, turbulent flow helps reactions happen faster.
Wow. So the same fluid can act so differently depending on the situation. How do engineers predict which type of flow will happen? I think I remember something about a Reynolds number.
You're sharp. The Reynolds number is a value that helps us predict and classify flow types. It takes into account things like the fluid's thickness, viscosity, its speed, and the size of the pipe it's flowing through.
So a high Reynolds number means?
More likely be turbulent, lower number, probably laminar. And by changing things that affect this number, engineers can design systems that get the type of flow they need.
So it's all about understanding how those factors work together. Sounds complicated.
It can be, but that's what makes fluid mechanics so cool. And the more we explore, the more we see that these concepts have real-world effects on safety, efficiency, and even our everyday lives.
All right, bring on the complexity. You mentioned that understanding fluid dynamics is essential for things like airplanes. Let's dig into that. How does all of this relate to big, complex systems?
That's where it gets really fascinating. We're about to enter the world of Bernoulli's principle, one of the most fundamental and cool principles in fluid dynamics.
All right, I'm ready. Lay on me. What's Bernoulli's principle, and how does it explain how planes can fly?
Bernoulli's principle says that as the speed of a moving fluid increases, the pressure within the fluid actually decreases. It sounds kind of backward, but it's one of the most powerful forces out there.
Wait, so faster-moving fluids have lower pressure. How's that possible?
It all comes down to energy. Imagine fluid flowing through a pipe. As it speeds up, its kinetic energy, the energy of movement, increases, but energy can't just appear out of nowhere, right? So that increase in kinetic energy has to come from somewhere.
So it's like it borrows energy from something else.
Exactly. It borrows it from the fluid's pressure. As the speed goes up, the pressure goes down to make up for it.
Okay, I think I'm starting to see it. But how does this make a plane fly?
Think about the shape of a plane's wing. It's designed to force the air to move faster over the top surface than the bottom. Because the air is zipping over the top, its pressure is lower.
And the higher pressure underneath pushes the wing upward, creating lift.
You got it. That pressure difference, caused by the difference in airspeed, creates the lift force that fights against gravity and keeps the plane up in the air.
That's mind-blowing. One principle explained how these giant, heavy machines can fly.
Yep. And Bernoulli's principle isn't just for airplanes. It's everywhere. The curve of a baseball, how a perfume atomizer sprays, even how some animals move through water.
Wow. So something as simple as spraying perfume uses the same principle that keeps jumbo jets in the sky. That's incredible.
Fluid mechanics is full of those aha moments, and we're just getting started. There's still so much to explore. Different types of pumps, turbines, and even how fluids interact with solids.
Well, I'm definitely ready to learn more. You said earlier that understanding how fluids act when they escape from containers is also crucial for safety. What can you tell me about that?
That brings us to Torricelli's law. It might sound intimidating, but it's actually pretty simple. It basically says that the speed at which a fluid flows out of an opening in a container depends on how high the fluid is above that opening.
All right, let me see if I get it. If I have a milk carton that's completely full and I poke a hole near the bottom, the milk will squirt out faster than if the carton was almost empty. Right?
Precisely. The height of the milk, or what we call the head, is greater when the carton is full. That means there's more pressure pushing the milk out of the hole.
Makes sense. I'm guessing this law applies to more than just milk cartons, though.
You got it. It has real-world applications way beyond milk cartons. Engineers use Torricelli's law to calculate things like how fast a liquid will drain from a damaged tank or how quickly water will rush out of a broken pipe. This information is vital for designing safety systems and figuring out how to respond to emergencies.
So if there's a leak in a chemical storage tank, knowing how quickly the chemical will spill out can help emergency responders contain the situation more effectively.
Absolutely. And sometimes knowing this can be the difference between life and death. For example, think about a fire in a building with a sprinkler system. Knowing the flow rate of water from the sprinkler heads is essential to ensure the fire is extinguished quickly.
Wow, that's pretty powerful. So even a seemingly straightforward principle like Torricelli's law can have a massive impact on safety.
Absolutely. That's the beauty of fluid mechanics. It's full of these amazing connections between things that seem totally unrelated.
Okay, so we've talked about pressure, flow, and how fluids behave when they escape from containers. What else is important to know about how fluids move?
Well, there are two main ways fluids can flow: laminar and turbulent.
Oh, I remember those terms from my physics days, but
Right.
I could definitely use a refresher. What's the difference between laminar and turbulent flow, and why does it matter?
Picture a calm, smoothly flowing river. The water is just gliding along in these parallel layers, barely mixing at all. That's laminar flow. It's smooth, predictable, and efficient.
So it's like everyone's marching in a perfectly organized parade.
Exactly. Now imagine that same river, but it's a raging torrent during a flash flood. The water is all churned up and chaotic, with whirlpools and eddies swirling everywhere. That's turbulent flow.
Oh, I get it. Turbulent flow is like a mosh pit at a rock concert. Everyone's bumping and crashing into each other.
Exactly. It's a great way to picture it. And just like sometimes you want a well-organized parade and sometimes you want the excitement of a mosh pit, there are times when we want laminar flow and times when we need turbulent flow.
Okay, so when would we want each type of flow?
Well, in many engineering applications, we try to achieve laminar flow because it's more efficient and predictable. For example, think about pipelines transporting oil or gas. We want the flow to be smooth to reduce energy losses caused by friction.
So smoother flow equals less wasted energy.
Precisely. And less wear and tear on the pipes themselves. On the other hand, sometimes we actually need turbulent flow. For instance, in a combustion engine, we want the air and fuel to mix thoroughly for efficient burning.
So turbulence can actually be a good thing. It helps mix things up.
You got it. And in some cases, we even deliberately create turbulence to enhance certain processes. For example, in chemical reactors, turbulent flow can help promote reactions by bringing the reactants into close contact.
That's interesting. So the same fluid can behave in completely different ways depending on the situation. How do engineers predict whether a fluid will flow smoothly or become turbulent? I vaguely remember something about a Reynolds number.
You have a good memory. The Reynolds number is a special value that helps us predict and categorize different flow types. It takes into account things like the fluid's viscosity, its thickness, its velocity, its speed, and the size of the pipe or channel it's moving through.
So a high Reynolds number means
It's more likely to be turbulent flow. A lower Reynolds number suggests laminar flow. And by adjusting the factors that affect this number, engineers can design systems to get the flow pattern they need.
So it's all about understanding the factors that influence flow and how to manipulate them. It sounds pretty complex.
It can be, but that's what makes fluid mechanics so fascinating. And as we continue exploring this world, you'll see how these seemingly abstract ideas have huge impacts on things like safety, efficiency, and even how we live our everyday lives.
Well, I'm definitely intrigued, and I'm ready to dive deeper. You mentioned at the beginning that understanding fluid dynamics is crucial for things like airplanes and heavy machinery. Let's get into that now. How does all this relate to these bigger, more complex systems?
That's where things get really interesting. We're going to step into the realm of Bernoulli's principle. It's one of the most fundamental and fascinating principles in fluid dynamics.
Okay, I'm ready. Tell me all about it. What is Bernoulli's principle, and how does it explain how planes can fly?
Bernoulli's principle says that when the speed of a moving fluid increases, the pressure inside that fluid actually decreases. It might sound a bit counterintuitive, but it's one of the most powerful forces in nature.
Hold on. Are you saying that faster moving fluids have lower pressure? How does that work?
It has to do with the conservation of energy. Think about a fluid flowing through a pipe. As it speeds up, its kinetic energy, the energy of movement, increases. But energy can't just appear out of nowhere. That increase in kinetic energy has to come from somewhere.
So it's like it borrows energy from something else.
Exactly. And that something else is the fluid's pressure. As the fluid speeds up, its internal pressure decreases to compensate for the increase in kinetic energy.
Okay, I think I'm starting to grasp it. But how does this explain how planes can fly?
Think about the shape of an airplane wing. It's designed in a way that forces air to move faster over the top surface than underneath the wing. Because the air is moving faster over the top, the pressure there is lower.
And the higher pressure underneath the wing pushes it upwards, creating lift.
You nailed it. That difference in pressure, created by the difference in airspeed, generates the lift force that counteracts gravity and keeps the plane in the air.
That's incredible. So this one principle explains how these massive machines weighing tons can stay up in the air.
It does, and Bernoulli's principle isn't just limited to airplanes. It's at work in so many other things. The way a curveball curves in baseball, the way a perfume atomizer sprays a fine mist, even the way certain animals swim through water.
Wow, I had no idea. So spraying perfume and a jumbo jet staying in the sky use the same principle. That blows my mind.
Fluid mechanics is full of these amazing connections, and we're really just scratching the surface. There's a whole world of pumps, turbines, and how fluids interact with solids waiting to be explored.
I'm ready to keep learning. We've only just begun to uncover the mysteries of fluid mechanics, and I can't wait to see what else we discover. Welcome back to Key Safety Talks. Before the break, we were right in the middle of unpacking Bernoulli's principle, and you were about to tell me about some other cool examples of where it pops up in the real world.
You bet. It's pretty amazing how this one principle shows up in so many unexpected places. We talked about airplanes, but Bernoulli's principle is also at work in things like carburetors, those perfume atomizers you mentioned, and even in the way some animals move through water.
Okay, let's start with carburetors.
Yeah.
How does Bernoulli's principle help an engine run?
All right, so a carburetor's job is to mix the right amount of air and fuel for combustion in an engine. And it uses something called a venturi to do this. A venturi is basically a narrow section in the pathway where the air flows.
So it's kind of like when we talked about constricting the flow with your thumb over the garden hose.
Exactly. As the air squeezes through that venturi, it speeds up. And because of Bernoulli's principle, when the airspeed increases, the pressure drops. That lower pressure creates a vacuum, and that vacuum sucks fuel up from a reservoir and mixes it with the air.
So it's like the faster moving air creates a suction that pulls the fuel in.
You got it. It's a pretty ingenious way to use fluid dynamics to make sure the engine is getting the perfect air-fuel mix to run smoothly.
That's really clever. Now, how about perfume atomizers? How do those use Bernoulli's principle?
Okay, picture this. You've got a bottle of perfume, and there's a little tube submerged in the liquid. There's also a bulb that you squeeze, and that creates a jet of air. When you squeeze that bulb, you're forcing air to move really quickly over the opening of that tube.
So we're speeding up the airflow again, right?
Right. And as that air zips over the opening, the pressure drops, just like Bernoulli told us. And that drop in pressure, that creates a vacuum, which pulls the perfume up the tube and out through a tiny nozzle. That's what makes that fine mist we all know and love.
It's amazing how such a simple little device can harness such a powerful principle.
It is. And nature also uses Bernoulli's principle in some pretty amazing ways. For instance, some fish, like tuna and sharks, use the shape of their bodies and fins to create areas of low pressure as they swim.
So they're kind of like living, breathing airplanes. They generate lift to help them move through the water.
Exactly. And of course, birds use Bernoulli's principle too. The shape of their wings allows them to control the airflow and pressure to generate lift for flight.
It's mind-blowing that the same principle that explains how perfume atomizers work also explains how sharks swim and jumbo jets fly. It really shows how interconnected everything in the natural world is.
I completely agree. And it just goes to show how important it is to understand these fundamental principles, not just for engineers and scientists, but for anyone who wants to understand how the world works.
Okay, I'm convinced. Bernoulli's principle is officially cool. Now, remember when we talked about laminar and turbulent flow earlier? Are there any real-world examples where not understanding these different types of flow led to, well, accidents?
Absolutely. There's a really tragic example that happened at a water park in Kansas City a few years back. There was a terrible accident on a water slide, and it turned out that the design didn't fully account for how water flow could change from smooth to turbulent.
Oh no, that sounds awful. What happened?
The slide was called verrückt, which means insane in German. It had this really steep drop, followed by a horizontal section where the riders were supposed to experience a moment of weightlessness. But the design didn't fully consider how the water flow and pressure would change as people went down the slide at high speeds.
So where did things go wrong?
Well, as riders went over that big hump, the water, which was flowing smoothly in a laminar way at first, suddenly became turbulent. It was unpredictable and chaotic, and that made the rafts carrying the riders really unstable. They started to oscillate violently, and tragically, in this case, one of the rafts actually went airborne.
That's just heartbreaking.
It was a truly devastating accident, and it really underscored how critical it is to understand fluid dynamics when designing amusement park rides. Even what seem like minor miscalculations or oversights can have catastrophic consequences when you're dealing with the forces and speeds involved in things like water slides.
It's a sobering reminder that even with the most carefully engineered systems, things can still go wrong. Pipes can burst, pumps can fail, and accidents do happen. What are some ways to minimize risks in systems that work with fluids?
You're right, we can never eliminate risk entirely, but we can take steps to reduce it. That's why it's so important to design in safety features and redundancies. One example is something called a pressure relief valve, which is a critical part of many hydraulic and pneumatic systems. Think of it like a safety valve for pressure. If the pressure builds up too high, the valve opens and lets some of it escape, which helps prevent damage or explosions.
So it's like an escape route for the pressure if things start to get too intense.
Exactly. And in systems where leaks could be really dangerous, like those carrying hazardous chemicals, they often use double-walled tanks or pipes with special leak detection systems. It's all about adding extra layers of protection.
It's like designing and operating systems that involve fluids requires a lot of careful thought. You have to think about pressure, flow, temperature, and all the ways things could go wrong. It can feel a bit overwhelming.
It's true, it can be complex, but that's why it's absolutely crucial to have a good grasp of the fundamental principles of fluid mechanics. Knowing this stuff empowers us to make smart choices, build safer systems, and respond effectively when something unexpected happens.
Well, you've definitely given us a lot to think about today. From the intricacies of Bernoulli's principle to the importance of safety features in fluid systems. Is there anything else our viewers should know about hydrostatics and hydraulics, especially when it comes to staying safe?
There's one area that people often overlook, and we haven't really talked about it yet. It's this concept called discharge coefficients.
Okay, I have to admit, I've never heard of that.
Ah.
What are discharge coefficients, and what do they have to do with safety?
Imagine you have a tank that's under pressure, and it has a small opening, like a valve or a nozzle. When you open that valve, you'd naturally think the fluid would flow out at a certain rate based on the pressure inside the tank, right?
Yeah, that makes sense. Higher pressure, faster flow.
Right. But here's the thing. In the real world, the actual flow rate is often less than what you'd calculate if you only considered the pressure. That's where these discharge coefficients come in.
So it's like a correction factor, like a reality check on our ideal calculations.
Precisely. The discharge coefficient accounts for things like the shape of the opening, how much friction there is inside the valve or nozzle, and even the thickness or viscosity of the fluid itself.
So if you don't factor in this discharge coefficient, what happens?
You could end up with a flow rate that's way off, and that could lead to some serious problems. For example, think about designing a fire suppression system. If the discharge coefficients for the sprinkler heads aren't calculated correctly,
Oh, that means...
the sprinklers might not put out enough water to actually extinguish a fire, or it could take way longer than you'd expect for them to kick in, giving the fire more time to spread.
That's a terrifying thought. So even though these coefficients seem like tiny details, they can have huge implications for safety.
They absolutely can, and this brings up another super important point: the need for precise data and meticulous calculations. When you're designing anything that works with fluids, you can't just wing it or rely on rough estimates. You need to have accurate measurements, use reliable formulas, and really understand the underlying principles.
It's kind of like that old saying, measure twice, cut once. But in this case, it's more like calculate carefully, design safely.
I like that. That attention to detail can really be the difference between a successful project and a potential disaster.
You've given us a lot to think about today. From the ins and outs of Bernoulli's principle to those tiny but crucial discharge coefficients, it's clear that fluid mechanics is a complex and amazing field. What would you say is the most important takeaway for our viewers?
I'd say the biggest takeaway is that fluids are everywhere, and they can be both beneficial and incredibly dangerous. Understanding how they work is essential for keeping people safe, making things work efficiently, and just appreciating how intricate the world really is.
Well said. That understanding could be the difference between being amazed by a bird in flight or witnessing a terrible accident that could have been prevented.
You got it. Whether you're an engineer designing some complicated hydraulic system or just a homeowner trying to fix a leaky faucet, knowing a little bit about fluid mechanics can help you make better decisions and solve problems.
I couldn't agree more. Now, before we wrap up this episode, is there anything else you want to share with our viewers? Any last bits of wisdom about the world of fluids?
I think it's important to remember that fluid mechanics is a field that's always evolving. There's always something new to learn, new discoveries being made, and better ways to use our knowledge to solve real-world problems.
So it's not just about memorizing equations and principles, it's about being curious and always searching for new information.
Exactly. Fluid mechanics is an exciting, dynamic field. I encourage everyone to keep exploring and asking questions, never stop learning.
That's excellent advice. I know I've learned a ton today, and I'm sure our viewers have too. We're almost out of time for this episode, but I want to thank you for sharing your expertise with us today.
It's been my pleasure.
And to all our viewers, thanks for joining us on this journey into the fascinating world of hydrostatics and hydraulics. We hope you found it informative and interesting.
We hope you'll join us again next time as we continue to explore the science of safety.
Until then, stay curious, stay safe, and keep those fluids flowing in the right direction. Welcome back to Key Safety Talks. We've been on quite a journey exploring the world of fluids, haven't we? From those unexpected hydrostatic pressure behaviors to that mind-bending Bernoulli's principle.
It really has been an exciting ride so far. And you know what? We've really only just scratched the surface. There's so much more to discover in this fascinating field.
You mentioned something before the break, another important aspect of fluid mechanics, something we haven't talked about yet, that's often overlooked. What did you have in mind?
One area that really deserves more attention, especially when it comes to keeping things safe, is how temperature affects the way fluids act. We've spent a lot of time talking about pressure, flow, and velocity, but temperature is a key player in all this too.
Oh, that's interesting. I know heat makes fluids expand, but how does that affect safety in, say, A hydraulic system.
Well, let's imagine a hydraulic system that controls the brakes on a big truck or the arms of a giant excavator. Those systems depend on precise pressures and flow rates to operate safely and do what they're supposed to do.
So what happens if the temperature of the hydraulic fluid changes a lot? Does it throw everything off?
It absolutely can. If the fluid gets too hot, it expands, which means the pressure inside the system goes up. And if it goes up too much, beyond what the system was designed to handle, you could have leaks, damaged components, or even a total system failure.
So it's like a pressure cooker then. The hotter it gets, the higher the pressure. And if it goes too high, things could burst.
That's a great way to think about it. And it works the other way, too. If that hydraulic fluid gets too cold, it gets thicker and more resistant to flow. We call that more viscous.
So it flows slower, like honey that's been in the fridge.
That's it exactly. That thicker, more viscous fluid makes it harder for the system to work the way it should. You might get sluggish performance or even a complete shutdown. And in a critical system like brakes, well, that could be disastrous.
Yeah, that's a little scary to think about. I hadn't really considered how temperature changes could have such a big impact on things like hydraulic systems. So how do engineers deal with that? Do they just build systems with super strong materials that can handle any temperature?
Choosing the right materials is definitely important, but it's just one part of the solution. Engineers use all sorts of strategies to manage those temperature effects in fluid systems. A common one is to include temperature sensors and controls in the design. Those can adjust the pressure or flow rate to make up for any temperature changes.
So it's like having a thermostat for your hydraulic fluid, keeping it within a safe temperature zone.
Precisely. And sometimes they use special types of hydraulic fluid that are designed to stay at a pretty consistent viscosity even when the temperature changes a lot. They don't thin out too much when it's hot or get too thick when it's cold.
Wow, I never realized how much thought and engineering goes into something as seemingly simple as managing the temperature of fluids. It really makes you appreciate how all these factors can affect a system's performance and safety.
It really does. And it highlights how interconnected all the different areas of engineering are. Fluid mechanics, thermodynamics, materials, science, they all work together to make sure things are built right and operate safely and reliably.
Okay, so we've talked about the impact of temperature on fluids. Anything else about hydrostatics and hydraulics that you think is especially important for safety?
One thing that's often overlooked is the importance of regular maintenance and inspection. As systems get older, the parts can wear down, seals can start to leak, and even the fluids themselves can degrade over time.
So it's not enough to just design it right from the start. You need to keep an eye on it and make sure it's still working the way it should as it ages.
Absolutely. Regular checks, preventative maintenance, and replacing any worn-out parts in a timely manner are all essential to keep fluid systems running safely and reliably for the long haul.
That's a great reminder for all of us, whether we're dealing with industrial hydraulic systems or just the plumbing in our homes.
You got it. A little preventative maintenance can save you a lot of trouble and expense down the road, not to mention help prevent potentially dangerous situations.
All right, well, we've covered a lot of ground in this deep dive, from the basics of pressure and flow to the complexities of Bernoulli's principle, discharge coefficients, and the importance of temperature. It's been an amazing journey into the world of hydrostatics and hydraulics.
I hope our viewers have come away with a better understanding of how these concepts are vital to so many parts of our lives. It affects everything from the safety of our homes and vehicles to how complex industrial processes operate.
I know I've definitely gained a whole new appreciation for the power and complexity of fluids. But before we wrap up, is there anything else you'd like to share with our audience? Any final thoughts?
You know, one of the most important things to keep in mind about fluid mechanics is that it's always evolving. There's always more to learn, new discoveries to make, and new ways to apply our knowledge to solve real-world problems.
So it's not just about memorizing a bunch of formulas and principles. It's about staying curious, asking questions, and being open to new ideas.
You hit the nail on the head. Fluid mechanics is an exciting field, always changing and challenging us. Keep exploring, keep asking those questions, and never stop learning.
That's great advice. I know I've learned so much today. It's been a really enlightening conversation. Thanks for joining us.
It's been my pleasure.
And to everyone watching, thank you for joining us on this exploration of the amazing world of hydrostatics and hydraulics. We hope you learned something new today, and maybe you even developed a new appreciation for the fluids all around us.
Remember, fluids are everywhere, and understanding how they work can make us safer, more informed, and more connected to the world around us.
Couldn't have said it better myself. Until next time, stay curious, stay safe, and keep exploring.